Greetings, and welcome to part 3 of developing your engineering intuition of structures. And today we're going to be drawing some parallels between beams and trusses. So basically, the first thing that we're going to do is take a look at some examples. And I have 4 examples that we'll go over. And the first example is probably what you're sick to death of already. It's just a simply supported beam with a load in the middle. Alright. Now I've modeled it as the beam in SAP, but I've also modeled it in a similar way with shell elements. And shell elements are pretty much just kind of like beam elements, except they have an additional thickness in the vertical direction. So we can actually visualize the stress distribution in the shells in order to tell us what the true stress distribution is in the beam. Now the third way I've modeled it is basically like a truss. This is also called a strut and tie model. So pretty much I have hinge joints at each point, and each one of my frame elements is just kind of a singular member pretty much. Alright, so the first thing we're going to do is take a look at the shear force in our beam. So let's check out the shear, and pretty much like you might expect, we have a negative constant shear on the left half that transitions to positive constant shear on the right hand side. Now we can visualize the shear stress, or the tau xy, which is listed as S12 in our shell elements, like so. Now pretty much we have most of our shear pretty much being constant on the left hand side, and then it transitions into negative shear. It just has a different sign convention for shell elements on the right half. So constant shear, and then it changes sign, and then it's constant again. Now what does this look like if we were to look at this in our truss? Let's check out the axial force diagram for our truss, and this is really cool. Now, you can use an interesting heuristic that says that the shear in a beam is carried by the tendons or the webbings of a truss. Well, what does that mean? Well, let's say we had that constant negative shear on this left-hand side. We would expect that the forces in our members, or more specifically the forces in our tendons, would remain constant because the shear force is constant. And indeed that is the case. Check it out. So all of these tendons carry more or less, visually it appears, the same load. And then remember how we transition from negative shear into positive shear right here on the right half portion? Notice how the tensile tendons are pointing down, going this way, and the compressive cords go up like this. Well, that's pretty much true for this whole left half portion until we get to the right half side of the bridge where it flips. Now our compressive tendons are going down and our tensile tendons are going up. And it remains constant on that side of the bridge as well. So, interesting. Our tendons carry the equivalent shear force carried by a beam. Now, let's check out the moment in our beam. And pretty much it goes from 0 at the ends to a maximum right in the middle. Now, what does this look like in our shell element model? It looks like this. So we're going to model the S11 or sigma XX stress, which is basically the axial or longitudinal stress in the beam. And the distribution looks like this. So we basically have near 0 axial stress at the ends, and of course 0 axial stress along the neutral axis of the beam. But at the extreme top and bottom fibers of the beam, we increase in compressive stress to a maximum right at the top. And on the bottom tensile fibers of the beam, we increase to a maximum tensile stress at the bottom of the beam. And it's a linear transition between compressive stress at the top down to tensile stress at the bottom of the beam. What does this look like with our truss? Well, let's check it out. Pretty much, we can use a similar heuristic to how we said that the shear in a beam is carried by the tendons. Well, in this case, now I'm going to say that the moment in a beam is equivalently carried by the top and bottom chords of a truss. Alright, so what does that mean? Well, pretty much like we saw in our stress distribution on our shell elements, in the top extreme fiber of the beam, we went from 0 stress to a maximum compressive stress. And linearly, in a similar fashion, we see exactly the same thing in our top chords. We go from near 0 compressive force in our top chords, ramping up linearly to max compressive force right in the middle. Same thing with the tensile chords on the bottom of our truss, since we went from 0 to max tensile stress at the bottom of our beam. So we can use that same heuristic to analyze the next model. And in this example, we're just going to look at a simple cantilever beam. And in this case, I basically have a point load on the end, so that means our shear force should be constant throughout the beam. And if we look at that in the shell model, that means that basically our shear is constant throughout the beam, more or less. Now let's check out, that would have to mean that pretty much all of our tendons carry pretty much the same force, and indeed that is the case. And because it doesn't change sign, it's the same sign, our tensile cords are always pointing down, and our compressive cords are always going up throughout the whole thing, and it's constant. So cool, that's correct. Oh, this is working out better than I'd hoped. All right. Now let's check out the moment in the beam. Pretty much we have 0 moment at the end, and then it ramps up linearly to a maximum moment value right at the support. Now with our shell elements, check it out. We're going to look at the S11, our sigma XX. So again, we have 0 axial stress along the neutral axis, and we have pretty much no axial stress right at the end of the beam, but along the top fiber, we see that it increases linearly to a maximum tensile stress, because we're looking at a cantilever beam. Now the tension is on the top and compression is on the bottom. Maximum compression and maximum tension right at the supports. So what does that look like for our truss with axial forces? All right, it looks very similar, but remember how I said that compression was always on the top and tension was always on the bottom? I lied. It's different in this case. So now we have basically our tension is on the top, because in the previous cases we had positive moment. We were always looking at beams that were in positive moment, but now we have a beam that's in negative moment. So it's flipped. Now tension is on the top and compression is on the bottom. So be aware of that. So again, we have 0 axial stresses in our beams, and they ramp up linearly to maximum values on the top and bottom chords, and tension on the top, compression on the bottom respectively, right at the support, just like we would expect and like we saw in the stress distribution here. All right, next example. This one is a little bit interesting, I think. So let's check out the actual loading. It's pretty much just like a 4-point bending test. So we have 2 supports at the ends, and then we have 2 equal loads right here and here. So that means that pretty much what we're going to see is a region where we have 0 shear in the beam. Why is that? Well, because we have a constant moment region, and I'll just kind of quickly show the moment diagram. So the moment is constant along this region in between those 2 points. And that pretty much means, since shear is the derivative of moment, then the derivative of a constant is 0. So the shear is 0. All right, so if that's the shear, we basically have negative, 0, and then positive. What does this look like with shells? Look at the shear stress, and yeah, we go from a constant, and again, the sign convention is flipped, but it's positive, and then 0, and then it's negative. So that would mean that when we look at this with our axial force diagram in our truss, we have a constant, and then 0. 0 shear pretty much means our tendons carry nothing. That's really cool, I think. I don't know. I think it's cool. Maybe you don't, but whatever. And check it out. When we change sign, we go from tension going down, compression going up, to flipped. Now compression's going down and tension's going up. Really cool. Same thing. Let's quickly go through the moment. And remember, we had linear increase to a constant moment region, which basically means that in our shell model we would expect to see a constant region of compressive stress right in the middle, and a constant region of tensile stress right in the middle on the top and bottom fibers of the beam, respectively. And of course, 0 axial stress throughout the neutral axis of the beam. Now, what does this look like if we do our axial forces? It basically means that our top and bottom chords carry virtually the same loads within that region. So it was constant axial stress along the top and bottom fibers of our beam, so that means our top and bottom chords will carry more or less constant compressive and tensile loads, respectively, on the top and bottom of our truss. Oh, wow, it's really working great. This is fantastic. Okay, now the last example. Let's check out shear force, but first, actually, I'm going to show what the actual loading is. It's basically kind of like we have a simple span with a cantilever on the end. You can think of this kind of like our bridge from 2013, where we pretty much had this little nice cantilever with a load on here, and then we have a load in the middle backspan location of the bridge. So our shear in the bridge is going to look like this. It's going to be negative, and just jump up to pretty big and positive, and then it's going to go negative. So what does this look like for shells? Well, the shear stress distribution, oh my god! Oh, it's a double rainbow! A double rainbow all the way across the bridge! What does it mean? Well, what it means is we basically have a positive shear here, and then it transitions into negative, and then it goes back to positive. Alright, that's what it means. Okay. I'm having too much fun. Let's go to axial. Alright, so that means pretty much in this region, constant shear, and then it changes signs. So tension going down, now comes up, and it's constant again in this region. And then it changes sign again. So tension going up, now comes down, and then it's constant for this last region as well. So everything is working out perfectly. I couldn't have planned it better. Let's check out the moment. So now it goes from 0 to a max positive value here, and then it transitions. So we go from positive to 0, and then it goes up to negative, a maximum value right at the support, negative moment. So we go from maximum positive to max negative, and then back down to 0. And so what does that look like with our shells? Well, for old time's sake, let's check it out. So we have a maximum compressive stress in the top fiber of our beam that goes to near 0 compressive stress right there at that transition point, and then it goes to now tensile stress in the top fiber of the beam, and then back down to 0. The opposite's true on the bottom. And so that would have to mean that for our truss, we go from pretty much compressive forces in the top chords and now down to a transition region where we basically have no stress or almost no axial force in our top chords, because we're transitioning from that region of positive moment to negative moment. So in that transition region, there's no moment, which means that our top and bottom chords carry nothing. And then it switches from compressive loads in our top chords to now tensile loads in our top members, and then up to a maximum, and then it goes back down. Again, opposite is true on the bottom. Wow, this is really cool. You can really take advantage of this, and I'll show you how you might be able to do that in a method that's called follow the moment diagram. Alright, so how do we take advantage of this? Well, check out the moment diagram. It looks kind of like this nice little triangle, and kind of like the joke that Convinde had brought up once, where one of his students in class had asked, Professor, how did that beam just become a truss? And then Convinde's answer was, of course, oh no, that's the moment diagram. And so everybody had a nice laugh. But no, seriously though, you can draw a truss that follows the moment diagram of a beam. Check it out. And it actually gives reasonably good results. Check out the axial forces, and they're almost pretty much comparable between the top and bottom chords. You're getting a lot of efficiency out of using this kind of method because you're only making your truss as deep as it needs to be in the locations where there's the most moment. So, on to the next example. Similarly, for our cantilever beam, we had 0 moment here and then a maximum here, so I'm just kind of drawing my truss to follow that moment diagram. And look at that, it looks really good. These are pretty much almost comparable forces. That's really great. Now, same thing with our beam here. Remember, we had a lamp up to a linear constant moment region here, and that's the same thing that I'm doing here. But remember, I technically shouldn't need to include these because there shouldn't be any shear inside of my truss in that region. So effectively these two members carry no force because there's no shear in my truss, but I need them in order to ensure that the truss is stable, because remember, these are pin joints. So if I took these out, the whole top assembly would pretty much flip around and do nonsense. Now the last example is probably the most interesting, I think, where basically we have our beam, remember, and then we went up to positive moment, dropped down to negative moment, and then went up to the end with 0. And you can kind of see how we follow the top chords in compression, and as they come down and they switch at that region where there's 0 moment, now it switches. So the top chords in compression, now the bottom chords are in compression, and the same thing with the tension coming up, it transitions. And like with the previous example, I technically could try to get rid of this member since it's not really carrying a whole lot, and because, I don't need that depth because there's basically 0 moment here, but I need it to ensure stability of the structure, because if I took it out, the whole thing again would probably just collapse and rotate around and do crazy shit. Alright, pardon my French. Well, hopefully that was really cool. I thought it was pretty awesome. Anyways, I'll see you guys next time.